So let's start with the course introduction and the discrete event systems and Petri Net's lecture. The contents of this lecture is, first of all, to explain thoroughly the aim of the course. You will see that the aim of the course deals with discrete event systems, discrete event models. I will explain you later what are they aimed for. And we will see, as an example, the Petri Net formulation. Because we will use the Petri Net formulation, we will use today the HPSim simulator. Is an open source simulation. We will use this simulator as the first simulation tool for our aim of this subject. The lab work will be connected with this simulation tool, and we will see the celebrated 5 Dying philosophers example. Well, first of all, what's the aim of the course? Here in this course, we will look at processes from a high level, from a high consideration level, because we will deal with production processes. As you can see here, we have a dyeing process, a textile process. We will consider, for example, the assistants in a shop. So we have customers, we have the customer's assistants, and so on. Here we have the emergency stage at a hospital, and here we have a mobile robot application. What do they all have in common? They all have in common that they will have, there will appear discrete events. What do I mean with this? That some things will happen in these processes depending on probability density functions. You don't know exactly when a customer will arrive to your shop. You don't know exactly when a patient will arrive at the hospital, at the emergency stage at the hospital. So you don't know when a new order arrives to your production process. So we will build this model, this discrete events model in my computer, in our computers, in order to get statistical results. Okay, here we have some histograms. These statistic results will help us in the decision-taking procedure. Obviously, because we have histograms, we have some statistics in here. All these processes, all these models will not be deterministic. So you will not have a single result, a single simulation result. You will have a probability density function as the output of the simulation of the system. So probability will be very important in our modeling. Let's start with the Monty Hall problem. This is only a simple example. Is it used very common on the internet, you will see, because the aim of this problem is to show you how important is probability when you take decisions. Well, the Monty Hall problem is based on a TV game show host, because, well, the name of the host was Monty Halperin. The name of the game show was Let's Make a Deal, okay? And, well, this is Monty Halperin. That's the Monty Hall problem. That's the reason for the name. And the next slides will use some pictures from the Ron Clark video. Well, let's consider that you are in a game, in a TV game show. The game show host tells you that you have 3 possible doors, okay? And you're expected to choose among these 3 doors. Behind these 3 doors, you have 1 car, but behind the other 2 doors, you have goats. Let's suppose that you wanna win the car. So you're expected to choose 1 out of these 3 doors. You don't know if the car is behind door number 1, door number 2, or door number 3. So you are asked to choose to pick up 1 out of these 3 doors. Let's suppose that you choose door number 3. Once you have chosen door number 3, the TV game host opens 1 out of the other 2 doors, okay? And he shows you that behind this other door, there is a goat. So now the question is, are you sure with your original choice? Well, keep in mind that the game show host knows where is the car. So maybe he is using the reverse psychology in order to trick you and make you choose wrongly. So, will you change your choice? Will you stack with your original choice? So let's have a look at all the possibilities that we have. First of all, if we stack with our original choice, we have 1 out of 3 probability to pick the car with this original choice, because you have 3 possible doors and there is only a single car behind 1 of these 3 doors. If you swap your choice now, at this moment, I don't know the probability to win the car. I will treat this later on. And you may think that there is no difference. Why? Because once this door has been opened, you have 2 possibilities. You have 1 car and 1 goat behind these doors. So you may think that you have the 50%. You have 1 out of 2 possibilities to pick up the car. So, what do you think? Shall we stack with our original choice, or shall we swap, or it makes no difference? Well, first of all, let's make some numbers about not swapping, about stacking with our original choice. Well, we have a 33% of probability to pick the car, okay, to choose the car. And we have 2 out of 3 possibilities to pick the goat. But the question is, what is the probability to pick up a goat on the first choice? Well, if you choose door number 2, you have 2 out of 3 possibilities to pick up a goat with this first choice. If you choose door number 1, you have 2 out of 3 possibilities to pick up a goat at the first choice. And the same goes for door number 3. So, let's suppose that we choose door number 3. And door number 2 is opened, so you know that there is a goat. Well, what was the probability to pick here at the first choice a goat? So what's the probability to be wrong at the first choice? The probability is 2 out of 3 possibilities. So if you swap your choice, you have a 66% of probability to pick up the car. So it's better to change your choice. Let's consider what it happens. Let's suppose that here we have a car. If we have here a car, obviously there is only one single car and three possible doors. So the possibility to pick a car in the first choice is only a 33%. So obviously with this 33%, if you swap your choice, you will get a goat, obviously. But the possibility to pick a goat at the first choice is double the possibility to pick a car with the first choice. So that's why it's better to swap, to change your choice. Well, this is because I want to show you that probability is very important in our decision-taking process. So that's the message I want to throw to you. You are expected in this subject to use probability considerations in order to take decisions on a problem. That's the importance of probability within this course. Which kind of systems will we deal with all along this course? Well, I suppose that you may remember that you have dealt with continuous systems. Remember, two tanks. Let's consider the level here in this tank. Here we have a pump, and then the level of this tank increases or decreases depending on the power of this pump. Okay? Some of you have studied discrete systems. Discrete systems are continuous systems that are controlled, regulated, or supervised by computers or microprocessor-based systems. That's why we talk about discrete systems. But here in this subject, we will talk about not discrete systems, but discrete-event systems, okay? Where changes in the states, changes in state variables will obey to random patterns. That means will obey on statistics. Afterwards, we will be able to tackle with embedded problems. What I mean with embedded problems, embedded systems, all of the above mixed up together. So production processes, as you can see here, computers, analog systems or continuous systems, and then discrete event systems. Well, what's the main example of a discrete event system? Toll roads. Here you have a toll, okay, and you don't know exactly when a car will arrive to this toll. Depending on the frequency, on the time lapse between car arrivals, you will have queues here in this kind of processes. So the interest of discrete event systems will be the study or the analysis of queues, bottlenecks, deadlocks. So the most important thing in discrete event systems will be the study of queues. Here you have the toll road, here you have a manufacturing process, production process, and here you have the queue in a supermarket cash section. We're going to use in this course the simulation in order to get these statistical results. Okay? As you may know, the simulation is the imitation of the operation of a real-world process or system over time. It requires a model. So the first part of this course will be the building of a discrete event model. This model gathers all the key characteristics or behaviors of our system. These models of the simulation in general is used in many contexts, is widely used. to show the eventual real effects of alternative conditions and causes of action. That's very important. Alternative conditions. Well, the main idea behind this course is that you will have a process, okay? This process will be modeled. You will get this model. But this model will not be a continuous model, will not be a discrete model, will be a discrete event model. Once we have this model, we will analyze some alternative conditions for this process. Before we check these alternatives on the real system, we will check all these alternative conditions in our model in order not to affect the real system. And once we have a good statistical results, then we will move these alternatives on the real system. So we're going to use this model in order to check some modifications, some alternatives on our system. And then when we are satisfied on the results of these alternatives, we will move all our proposals to the real system. Simulation is also used when the system is not accessible. For example, let's suppose that we are modeling a factory, a production process that is far away from our office. So we want to have like a reproduction of the behavior of our real system in our computer. So when we have the system that is not accessible, we have like a small reproduction of its behavior in our computer. Simulation is also used when we are dealing with a dangerous system or unacceptable to engage. And finally, simulation is also used when you are designing the process. Let's suppose that you are analyzing, like considering a new production chain. So when you are designing this new production chain, just before you apply, just before you acquire all the new resources, it's strongly recommended to make a simulation, to build a simulation model during this design process. What about these mathematical models? Well, as you can see here, this figure shows that the real system is quite complex. As you can see here, there are a lot of curves in here, so the real system is quite complex. If we want to have an accurate model, obviously this accurate model tries to explain all these particularities of the real system, okay? But what's the problem of the accurate model? The problem of the accurate model is the handling on its use. When a model is so complex, when you have model complexity, obviously is a better explanation of reality, as you can see here. But it results in a worse handling on its use. So sometimes it's better to have an accurate model. As you can see here, this model is so simple. This model explains in a simple form the behavior of this real system. But this model is very easy to handle. So in this subject, I will choose this kind of inaccurate models as a good approximation of the behavior of the real system. So obviously, the real system is one thing, and we will use like an inaccurate model to describe this real system. Which kind of models are we going to use? Obviously, the discrete event models, and the most celebrated example are Petri nets. This kind of modeling was invented in August on 1939 by Carl Adam Petri. He was a chemical engineer, okay? So the models were invented in order to describe chemical processes in such an easy form. As I told you before, I prefer easy, so inaccurate models, but in order to have a better handling on its use. These kind of models are directed and weighted graphs, and they have two kind of nodes, places and transitions. Some of you will have like a reminder of the state machines when you dealt with digital digital systems, okay? But here we have some differences, but they are quite similar to these state machines, okay? So we have places and transitions. Places will be represented as circles here in the diagram. Then transitions will be represented like this kind of bars. And places and transitions will be connected by these arcs. These arcs will connect a transition to a place or a place to a transition, but the arcs cannot connect the same type of elements in a Petri net. So you will not find an arc between two transitions or between two places. So always arcs will go from a place to a transition or from a transition to a place. Which are the meanings? What are the meanings of the places and transitions? Well, the places will represent the conditions of the system, the state of the system, and transitions will represent the events that may occur. The arrival of a customer, when some product is ready for expedition, is ready to be processed, when a patient arrives at the hospital, when the triage process of this patient has finished, and so on. So keep in mind, places are the conditions or the state of the system, while transitions are the events that will make the system change into a new stage. I'm going to explain it thoroughly later on. Let's have a look first of all at the machine shop example. Here we have some conditions, so states of the system, and these four are the events that may happen in our system. First of all, which are the conditions, the states for this system? Well, first of all, we have the state, the condition that the machine shop is waiting. So here we have the machine shop, okay? And the machine shop is waiting means that some product that needs to be processed in my machine shop will arrive and is waiting to be processed. This is the second condition for the system. So first of all, the machine shop is waiting. So we have the machine shop idle. That's the important concept. Idle. Here we are. So the machine shop is idle. So it's not busy. The machine shop is waiting for a new order to arrive. So then a new order arrives and is waiting. If the machine shop is idle, the order is being immediately processed. Then we have the next condition is that the machine shop is working on the order. And finally, the last state of the system is that the order is complete and out of the machine shop. Then obviously we go back to the initial condition when the machine shop is waiting for a new order to arrive. Which are the events that will make the system to evolve from one state to another state, to the next state of the system? Well, the first event is that an order arrives. Another possibility is that the machine shop starts on the order. The machine shop finishes the order, and the order is sent for delivery. So these are the events that may happen in our process. Let's check now how these conditions and these events can be represented in a Petri Net model. Well, first of all, I told you that the events are the transitions of the system. So an order arrives that is the first event will be represented as a transition, as you can see here. Then the condition of the system is the machine shop is waiting, an order has arrived and is waiting. So the second state, as you can see here, appears here. An order is waiting. So when an order arrives, this token, this element in here, appears here in this place, and that means that the state of the system is exactly that an order is waiting to be processed. At any time, the processing will start. So the machine shop will start on the order. But we have another condition for this starting of the process to happen. The other condition is that the machine shop is idle, waiting for work. That is the first condition. So if both conditions are accomplished, as you can see here, an order is waiting and the machine shop is idle, then at any moment the processing can start. And then this order will disappear from here and will appear in here, in this place, because the state of the system has changed. Obviously, the machine shop now will not be idle, will be busy, so this token in here also disappears. And here we have a single token. That means the order being processed by the machine shop. Once the processing is complete, then obviously the machine will be idle again and the token will appear here, and then this token will appear here because the order is complete. And then at any moment when the order is complete, the order can be sent for delivery. So that's the first representation of the machine shop example. Now, what's the difference between enabled and fired transitions? Let's have a look at these two situations. Here you have some condition, okay? Here we have the event T, the transition T. Here we have the condition that it's called P1, and here we have another condition. Let's check to this transition. We say that the transition T is enabled when there are enough tokens in the preconditions in here in order to satisfy all the conditions for this transition. Let's have a look at here. Here we have, in this arc, a weight of 2. And here we have a weight of 1. That means that for the process to be in the next stage, in the next state of the system, we need 2 elements in here, and we need at least 1 element in here. So at least 2 elements in P1 and at least 1 element here in the other condition. Obviously, we have 2 tokens in here, so there are enough tokens for this condition, and obviously here we have enough tokens for this condition because we have at least 1 token. So now we say that transition T is enabled. So at any moment, the system will change into the new stage. That's the meaning of enabling a transition. When a transition T is enabled, this means that all the preconditions of the state to change are accomplished. So you have enough tokens in the previous conditions for this transition to pass to get through the new stage. So let's remark the difference with a fired transition. When a transition is enabled, I told you that at any moment the system will change to the new state. And this moment depends on probability density functions, okay? So will depend on a probability density function. Then when this transition is fired, 2 elements here in place 1 will disappear, and then 1 out of these 2 elements in this other place will disappear, because here I have a weight of 1, and then 2 elements will appear here. Well, first of all, the first message is that this number is not forced to be the addition of these 2 numbers. This situation does not mean that the 2 elements that has disappeared from here and the single element that has disappeared from here will not be added, and here we are not forced to have a 3. Okay, let's think, for example, that we are cooking an omelette. Okay, we have a pan and we are going to cook an omelette here in this pan. Let's say, for example, that this is the pan. Okay, I have 2 pans in my kitchen. I have 2 frying pans in my kitchen, and these were the 2 eggs, because I want an omelette from these 2 eggs. Okay, so what do I need to start cooking my omelette? 2 eggs and a single frying pan. Okay, yeah, and now here I have 2 elements. Okay, I have the pan and the omelette. Okay, so I have 2 elements because I have mixed my 2 eggs into a single omelette, for example. Well, let's reinforce the concept about enabled and fired transition. As you can see here, this transition is enabled because I have enough tokens in here, enough tokens in here, and enough tokens in here. As you can see, once this transition is fired, 1 token will appear in P4 and 3 tokens will appear in P5. Because here I need 2, so 2 will disappear, so 3 minus 2 is 1. 1 minus 1 is empty, an empty place. And then here I have 4, so 2 will be remaining because I subtract 2 tokens from here. Here I have 1 single token, so once the transition is fired in here, 3 new tokens will appear, so here we have a 4, and here we have a 1, because originally this P4 was empty. Okay, let's go back to the example of cooking an omelette. Here we have the resources. Here I have a fork. Here we have the eggs. We have a dozen of eggs, okay, you can see here. Then here I have another resource that is salt, olive oil, my pan that it's so clean, sorry, and the cooker in order to heat up the pan. So what do I need for the cooking process? First of all, I'm expected to whiten the eggs. What do I need to whiten the eggs? A single fork, as you can see here, and 2 eggs, because I will cook an omelette from 2 eggs out of this dozen of eggs. Then at any moment, if I have a fork and I have enough eggs, at any moment I will fire this transition and I will beat the eggs. At any moment, depending on the speed and on the intensity how I am beating the eggs, then the eggs will be beaten. Okay? So then if I have salt, olive oil, a cooker, and a clean pan, I will start the cooking process at any moment, depending on probability. Okay? But this is not a deterministic time. So keep in mind, on discrete event systems, you do not have deterministic processes. You have processes depending on probability. Because, for example, beating the eggs, maybe you beat the eggs so quick, you beat the eggs with high intensity. Maybe I beat the eggs so slow. So depending on the human behavior, we have here different times in order to get through the eggs to be beaten state. So depending on the human behavior, you will have different probability density functions in your process. You will not know exactly when a new customer arrives to your shop. You don't know in your production process when a new order arrives, and you don't know when a patient will income to the emergency stage at a hospital. So we will study these kind of processes that are like equipped with probability density functions. Let's now talk about the formal definition of a Petri net. Well, first of all, here we have a diagram, a Petri net. As you can see here, a directed graph. Here we have some conditions, P1 in here, P2 in here. I don't want you to look at the specific name of the conditions. That's not important to me. Okay, at the end is only a diagram, okay, a Petri net diagram. And if we forget about the process that's behind this diagram, I want you to focus only on the formal definition I'm going to explain you in a while. First of all, we have P1, P2 here, we have P3, 4, 5, 6, and 7. So we have 7 places. And you can see here that we have the events in here, T1, T3, 2, 4. At the end, we have 6 transitions, 6 possible events in my system. So the formal definition of my Petri net will be, first of all, the places. So how places are here defined in my diagram. So here we have P1, P2, P3, P4, P5, 6, and 7. So that's the list of places in my diagram. Then we have the list of transitions. So first of all, conditions, and then events, transitions, from T1 to T6. As you can see here, I use curly brackets here in order to tell the reader that this is a list of places, and this is a list of transitions. And then the flow. What is the flow? First of all, the list of all the connections taking places as the origin and transitions as the target or destination. So let's have a look at P1. First of all, this list of elements are the weights that connect P1 with all the transitions. So for P1, we have 1, 2, 3, 4, 5, and obviously 6 possible connections to the 6 possible transitions that we have in here. So as you can see here, we have a single connection from P1 to a transition, and this connection goes to T1. So that's why P1 is only connected to T1. Okay? So that's why here in this list of numbers appears only here a 1. And why a number 1? Because by default, if you don't have a weight assigned to an arc, you can consider that here there is a 1. So the message is that from now on, if you don't have any number next to your arc, you can consider that 1 is the weight for this arc. Let's go to place number 2. Place number 2 is connected to transitions. So let's check which transitions place 2 is connected to. So P2, we have P2 in here, and it has only a connection to a transition. And this transition is T2, not T1, T2, because we are taking, first of all, in this flow, the places as the origin and the transitions as the destination or target. So for P2 is connected only to T2. That's why here we have a 0, 1, and the remaining numbers are 0. What about P3? The same goes for P3. P3 is only connected to T3. So for P3, we have only a connection to T3 with a default weight of 1 because there is no number in here. The same goes for P4, 5, 6, and 7 because all the places are only connected to a single transition. Let's go now for the second part of the flows. The second part is to take a transition as the origin and a place as the target or the destination. So we are considering these arcs. The arcs that has a transition as the origin and a place as the destination. Okay? So you will see that numbers are gathered in groups of 7. Why? Because we have 7 possible destinations, 7 places. And we have 6 gatherings, 1, 2, 3, 4, 5, and 6 gatherings of this number. Because we have 6 origins, 6 transitions. So let's go now for transition number 1 here, signal alarm. Transition 1 is connected both to P2 and P3. That's why transition 1 is connected to P2 and P3. That's why for P1 there is a 0, and for P2 and P3 we have both 1s. Because we have no weight in here and no weight in here, no specific weight. So by default, 1 and 1. And the same goes for transition 2, 3, 4, 5, and 6. Let's have a look at transition 6, for example. Transition 6, that is this, is connected to place number 6. That's why place 1, 2, 3, 4, 5, and 6. Finally, for the Petri Net definition, we have the initial marking. So, the initial tokens that are placed in our conditions. So, in other words, where are the tokens? Where are the tokens? Which is the initial state of the system, the initial marking of the system. As you can see here, we have 2 tokens in P1, 1 token in P5, and 1 token in P6. 2 tokens in P1, 1 token in P5, and 1 token in P6. All the remaining places here are empty. There are no tokens in these remaining places. Well, in Petri nets, it will happen the concurrency effect. Well, at the end, the concurrency means that for a transition to be enabled, several conditions must be accomplished. So if here we have a 1 by default and here we have a 1, we have 1 and 2 conditions to be accomplished before this transition T1 is enabled. The same goes for T2. We have 1 condition in here and another condition in here. So that's what we call concurrency of conditions. So several conditions that are applied for a system to have a change. What's the conflict? Well, the problem is that here I need 1 token in here, 1 token in here, 1 token in here, and 1 token in here. And we have 1 and 2 different processes. Okay, as you can see, we have 2 different events. We have 2 different transitions. But both transitions are in competition for this condition to be accomplished. So now, at this moment, with this initial marking, this condition, this A transition is enabled, as you can see here, because we have more than 1 token in here, and we have 1 token in here. And then for transition B, there are enough tokens in here and enough tokens in here. What it will happen? Depending on which transition fires at first, this token will be extracted from this place, and there will be appear, obviously here we have a 1 and a 1. This token and 1 out of these tokens will appear depending on which transition fires the first, here or here. And then let's suppose, for example, that transition A fires at first, so this token disappears, this token disappears, and a single token appears here. So we have a conflict because this is a common resource, a common condition for both transitions to fire, to be enabled. So the firing of transition A makes transition B to be not enabled because the token will be missing for this transition. So obviously the first that fires, the first that makes the other ones to be not enabled. So we have a conflict, and this is very typical in production processes. We have the same effect in the emergency stage on medical applications, on traffic jams, and the same, because we have the same resource that is shared by many people, many products, many cars on the road. So we have conflict because all the elements in my process are in competition for the same resource. So this is the main objective of this subject, to tackle with this problem, to tackle with conflicts when you have shared resources. And this is the aim of today's lab session, as you will see later on. This conflict will lead us to a mutual exclusion of processes. As you can see here, we have process number 1 and process number 2. Because both processes, these are production processes, both production processes share the same resource. When a process is working, this inhibits the other process to work. So when this transition is fired, it makes the other transition to be not enabled. So this process number 2 cannot go on if process number 1 is going on, is working. And the same the other way around, okay? The same goes for process number 2. If process number 2 is working, because it's using this resource, the shared resource, process number 1 cannot go on, cannot work, because this process number, the working of process number 2 inhibits process number 1 to work. So this situation will be very common because this situation is created by the conflict of sharing resources in all our systems. Well, what about the fork and join? Well, the fork, here we have a fork, as you can see, a common base, and the firing of this transition makes 3 processes to start, as you can see here. Here, I don't know what's behind here. Let's suppose that we have like a subnet here, sub Petri net, a small Petri net in here, but the join effect is that we have several conditions to be accomplished for a single transition to fire into a new state of the system. So these are the fork and the join effect. What about producers and consumers? Well, this is not mutual exclusion because we are not sharing a resource, but the consumer, the condition for the consumer to go on is that the procedure has already finished, okay? So when this transition is fired, let's suppose that this means idle, okay? Here we have idle, yeah? And here we have busy, okay? When the process ends, the machine becomes idle, and then the product is ready to be consumed here, is ready for the consumer. So that's a very common situation of a producer-consumer. So before a process starts, we need a previous process to be finished, to be ended. Let's now have a look at a very common and simple example. I have called it sharing the calculator. Let's suppose that we have a very specific calculator, and this calculator is shared by 2 students, okay? Here we have Peter and Mary, okay? They are both studying maths. Let's suppose that tomorrow they have an exam, a mathematics exam, and they are expected to use a very specific calculator, okay? But they only have a single calculator in order to prepare the exam, okay? If we have this initial situation, as you can see here, the calculator is a common resource for both students in order to do the calculations. Students will swap between 2 states. The states of the system are Peter is studying or Peter is doing calculations. Mary is studying, Mary is doing calculations. Obviously, they cannot both do calculations at the same time. Why? Because we have a single calculator, okay? So if Peter takes the calculator and goes through the new state in order to do the calculations, this will make this condition for Mary to be not enabled. So Mary cannot go through doing calculations until Peter has finished and delivered back the calculator. Okay? So that's the idea. And what's the problem on this? Well, the problem is that Mary is a very good student, is an outstanding student. Okay? Mary thinks the problem twice before she is doing the calculations. Okay? So the use of the calculator from Mary is a very small amount of time. So Mary spends a very small amount of time doing calculations because Mary is a very applied student, is an outstanding student. So Mary is thinking all the calculations before she takes the calculator and spends some small time doing these calculations. But Peter is not an outstanding student, okay? Well, this is only an example. It's only to make the difference between two students. Peter is a bad student, okay? He is not thinking twice, all the calculations. He's only doing the trial and error procedure, okay? Peter is taking the calculator so often, spends a lot of time doing calculations, and gets the calculator to be busy most of the time. Okay, that's the idea. So here we have a conflict because Peter is taking is making the calculator being so busy the most of the time. Okay, so Mary is in trouble with Peter because she cannot do the small time calculations because Peter is making the calculator, well, is using the calculator most of the time. So now we're gonna move to the simulator that we will use in today's lab session. Okay, you have in the documentation, you have the link in order to download this open source. Here, this is HP Simulator, is an open source simulator, and I'm going to show you this example in the simulator. Okay, I will zoom all this model. Okay, and here you have the initial situation. The initial situation is that Peter is studying, the calculator is idle, and Mary is studying. Okay, so no one is using the calculator, but both students have the calculator available. So at any moment, Peter can swap between studying and doing calculations. Mary at any moment can swap between studying, can switch from studying to doing calculations. Okay? The key point is that if you, at any moment of the simulation, you want to go back to the reset, to the initial marking of the system, you are expected to click on this reset button. Okay, so if you click here, you will see that the initial marking appears in here. Now I'm in the initial situation. Okay, let's have a look at this transition. Okay, this transition tells us that the minimum time that Peter is studying is 1 minute, as you can see here in the upper left section, 1 minute in here, and the maximum time that Peter is studying is 2 minutes, as you can see here. Now, at this moment, the value is 1. But what's the probability density function behind the behavior of Peter studying a uniform distribution. Okay, here you can choose between immediate, we're not going to use this, deterministic, we're not going to use this, but you can choose between exponential or uniform distributions. Okay, I will show you later on a different example, the 5 dining philosophers that use exponential probability density distributions. Okay, but now for this moment we have uniform, the minimum value, the maximum value, so the bounding values of the uniform, the minimum, the maximum, and the actual value. Okay, this value will change over time all along the simulation. Fine. What about Mary studying? I told you that Mary thinks twice all the calculations that she expects to do. So here, Mary is between 5 and 10 minutes studying, thinking about what to do. Okay, and now, well, this is a value that is out of this. This is because, well, I have this initial value, but it's not a correct value. Okay, the value must be between 5 and 10. Okay, so let's suppose 6. Yeah, and then let's have a look afterwards. What about the other process? How much time Peter is doing calculations? Here we are. Peter is doing calculations between 5 and 10 minutes, as you can see here. But on the other hand, we have Mary doing calculations only between 1 and 2 minutes. Why? Because, as you may remember, Mary thinks twice what she wants to calculate, what she wants to do, and that's why she spends a small time doing calculations. Okay? Well, so if you want to check the behavior of this system, we have this simulator that we can run for several times, and we will check the behavior of the whole system. But we know at the beginning that Peter will have the calculator most of the time. Okay, so in order to make this system to run, here you have this button. Now I am asked to save the changes. Okay, I will save the changes, and well, at first the diagram disappears. Okay, and here I have all the information about the simulation. But if you prefer to have a look at the window with the diagram, you can switch to this window. Okay, here, window, this window. Okay, and then you can start the simulation. You can run the model at any moment. Okay, obviously here we will run it fast, and here we will do it step by step. Okay, so let's now, obviously you can change the speed of the simulation. Here it means very fast, and here it means very slow. Okay, very fast and very slow. So let's now check the behavior of the system. At the beginning, both are enabled, but only Peter fires. Why? Because Peter spends small time studying. Now Peter is taking a lot of time doing calculations. So that's why this transition is enabled. Now here we have Mary waiting. Now, for a while, both are enabled again. Peter takes again, because Mary is still studying. Okay? She cannot use the calculator. So now, once Peter has finished calculations, we have now both again enabled transitions. Again, Peter. And if we increase the speed of the simulation, we will see the behavior of the system. Okay, Peter is still doing calculations, enabled, and most of the time, as you can see, Peter is doing calculations. I will increase the speed a bit more. Peter again, doing calculations, Peter again, and so on. Obviously, at any time, Mary will take the calculator and she will do the calculations. But as you can see, Peter is most of the time making the calculator so busy. So in today's lab session, you will be expected to build the same model but for a different example. You will see later on. Okay, I close this simulator and I will go on. Let's have a look now to a different example. Well, this is a manufacturing process example. It's about a textile process. Okay, and we are asked to build a Petri Net model on the packing section as the final stage of the yarn dyeing process. Okay, so in order to perform all process, we only have two available workers, A and B. Each one of them is able to execute a specific task. Worker A will be focused on coordination task and delicate work, and worker B will be focused on heavy work. Here we have two resources, worker A and worker B. The whole process is like this. Here we have a layout of the yarn dyeing process. Okay, here we have the input warehouse. Okay, so here we have the storage, yeah, and then yarn bobbins come from here. Then here we have the dyeing process. Okay, so yarn bobbins are colored in here. Okay, then because we have, once this process has ended, we have wet yarn bobbins. Okay, we have wet colored bobbins. So we have the hydro extracting in here and the drying section. So once the yarn has been dried, we need to spool all the yarn. So we change from original plastic bobbins into a final cardboard bobbins. And finally, we have here the packing section, this packing section that you can see here. And finally, we have the product finished and prepared for expedition. Okay, so we have the output warehouse in here. This was a real problem I was involved in about 18 years ago. Okay, and we're gonna use this problem like for many examples all along this course. Here we have the explanation. This was an exercise for an exam. Okay, so here we have the explanation of the process, and you were expected to build at the end the process, but in a Petri Net form. Okay, so first of all, yarn cones arrive in groups from the previous spooling section. Okay, so worker A does the quality control. At the end is the moisture, touch, and paraffin control on the finished yarn bobbins. Okay, so immediately after, worker A puts each single bobbin into a single plastic bag. After that, the same worker, so worker A, puts all the cones within the plastic bags into a single cardboard box. So let's have a view, let's have a look in here. Here we have the yarn cones arrival. This is one state of the system. Okay, the next state will be the moisture, touch, and paraffin control. Here we have the plastic bags. Here we have the cardboard box. Okay, and finally this process ends and the bobbins are already into the cardboard box. Okay, for all these sub processes we need one worker A. This is the resource worker A. Okay, so for this transition to be enabled, we need the arrival of the yarn cones and then the worker A to be idle. Then this transition is enabled. At any moment it fires, and then it goes through all these sub-process. Once this sub-process ends, we have the worker A again to be idle here in order to be shared, as you will see, with other section. Okay? Let's go now for the next stage. So once we have the bobbins in the cardboard box, let's have a look at the worker B incidence. The next stage is the waiting process, which is done only by worker B. Afterwards, the same worker, so worker B, levels the cardboard box aided by a computer. That will be another resource, as you can see here. Worker B idle, computer to be idle. Worker B continues with the sealing of the box. Okay, so here, once we have the bobbins already into cardboard box, here you are. Okay, then for the waiting process, leveling, and the sealing process, we need worker B. So that's why worker B is a precondition for this transition to be enabled. Okay, once this transition is enabled, so bobbins are ready into the cardboard box and worker B is idle, this token in here goes through the waiting process, leveling, and sealing. Okay, but be careful, for the waiting process, the worker needs to be aided by a computer. So that's why here I need the computer. Once I have finished the waiting process, I deliver back the computer to be idle again. Consider that there is this additional resource, the computer, used for the waiting and the following leveling process. Okay, so if you, the statement of the exam asks us for a modification of this behavior. If the computer is used for the waiting and the following leveling process, this must be erased from here, and this arc must be moved here, because both the waiting and the leveling process, they both use the computer. So this is a final modification on the model. So the first model is with the computer being delivered back from the waiting procedure, okay? But the final modification is, what am I expected to do if I consider that this additional resource, the computer, is used for the waiting and both for the, and also for the following leveling process. So here we are. This arc will be moved to the leveling. After that, both workers carry the cardboard box to the wrapping machine. The wrapping machine is this machine in here. Okay, that's the final stage of the process. And finally, they both cooperate in order to place the wrap box in the expedition deck. So after the sealing of the box, we have the box leveled and sealed. That's why after sealing, the worker B is delivered back to be idle. But we need both worker A and worker B for the wrapping machine, as you can see in here. And then they both do this process. And finally, once the cardboard box is on the deck, ready for expedition, they are delivered back to be idle. This is the final model, the whole model. As you can see, this whole model has a shared resource that is worker A and the shared resource that is worker B, because both processes, the final stage and the beginning and the middle stage, are using these resources. so we are in conflict. This final part of the process cannot be executed, cannot be run if worker A is on the first part of the process or if worker B is in the middle part of the process. So that's why we are in conflict. So for today's lab session, we will have a look at the celebrated example of the 5 dining philosophers. This is a classical example on how important are the shared resources that lead a system to mutual exclusion conflict situations. Okay? So let's consider that we have 1, 2, 3, 4, and 5 philosophers. These are 5 Chinese philosophers. The reason to be Chinese is because they are in front of a rice dish. They are eating rice. Well, the classical example is the 5 Chinese philosophers. Okay? Well, the important thing is that we have 5 philosophers eating rice. But they have 2 possible states. They can be philosophizing, thinking, okay? And they can be eating rice, okay? Because they are Chinese, they use chopsticks, okay? Every philosopher has 1 chopstick on the right, 1 chopstick on the left, okay? Because the philosopher is looking forward the rice dish. So this is the right hand of the philosopher, yeah? And this is the left hand chopstick for this philosopher. As you can see, this philosopher has chopstick 1 and chopstick 2 ready for use, ready to be used, okay? Philosopher 2 has chopstick 2 and chopstick 3 in order to eat rice. But as you can see in the figure, when philosopher 1 is eating, philosopher 2 cannot eat while philosopher 1 is eating. Why? Because philosopher 1 will use chopstick 1 and chopstick 2. So this makes philosopher 2 not to eat. This cancels the possibility for philosopher 2 to eat. Okay? The same goes for philosopher 3, because philosopher 3 has 2 chopsticks to be used, but if philosopher 2 is eating, philosopher 2 is using these 2 chopsticks, so then philosopher 3 cannot eat anymore. Okay? So the statement is, each philosopher alternates between thinking and eating according to some probability distributions, okay? On the time they spend doing the thinking and eating processes. To eat, the philosopher needs 2 chopsticks and he is only allowed to use the 2 which are placed next to him, okay, on his left and right side. The sharing of chopstick prevents 2 neighbors from eating at the same time. So, what are you asked about? First of all, 2 points. Draw the corresponding Petri Net diagram for this case study by pencil and paper. Okay, you're expected to draw in a piece of paper this corresponding Petri Net diagram. Okay? Afterwards, use a single piece of paper and put down your full names on it. Okay? The names of the team. Deliver it to the professor once you have finished. Well, deliver will be to take a photograph, okay, and upload this photograph in the task in the virtual campus, okay? Then, 6 points. Use HPSim simulator in order to view the previous diagram, the Petri Net, okay? And to set all the parameters in places and transitions to avoid deadlocks. The desire to eat, the time they spend thinking, okay, is considered exponentially distributed with a mean of 3 time units, and the time spent in the eating process can be modeled by a uniform distribution with a minimum of 2 and a maximum of 4 time units. Okay? Then finally answer these questions in a piece of paper to deliver. The questions are: can two neighbor philosophers eat at the same time? The answer is so obvious, okay? Why? You must justify your answer. And the most important thing, is there a possibility that a philosopher starved to death? Yes? No? And why? This is the end of the first session of this course, okay, this theoretical session. But what have I planned for the next session? What are we going to see on the next session? First of all, we will start with the Brest paradox. The Brest paradox at the end tells that the increasing number of resources does not always mean a better system performance, okay? I strongly recommend you to have a look at this video, okay? It's a very good explanation on this Brest paradox, okay? I'm gonna put the link in the description of this video. We will also have a look at how can we translate a Petri Net into MATLAB. This is a toolbox for the MATLAB environment, okay? So during this week, I'm going to tell you how to install MATLAB, how to install the Sim events toolbox, okay? Because next week, we're going to translate these Petri Nets into a Sim events model. The important thing is that the next session laboratory work will be to translate the dining philosophers problem in Sim events. So we will get some statistics on the simulation of this model.